Welcome to podcast 8.1. This is on chapter 8 stuff, which is all about bonding. A lot of that is going to be reviewed, so let's get right to it. What is a bond? It's simply a force that holds atoms together. And when we think about why, it all has to do in terms of energy, right? What is the driving force to cause two atoms or more atoms to come together? And it turns out that when atoms come together, it gives them a lower energy. So that is the driving force. Now this term right here, bond energy, we'll talk about this a little bit. Okay, the bond energy, and we're going to see some charts and stuff, is the energy that's required to break a bond. So imagine we've got something like water here, right? If you want to break this bond or break that bond, it's going to require a certain amount of energy. And so we will look on some tables and you will find out what an OH bond energy is in some kind of kilojoules per mole, and we'll go from there. But for right now, we want to focus on the fact that the reason that atoms will bond is to give that new compound a lower energy state. All right, on to ionic bonding. Again, this is some review. So we know that ionic bonds usually occur between metals, right, and nonmetals. And another way to think of it is metals like sodium tend to have a low ionization energy. In other words, it's easy to remove an electron to make a positive ion. And then nonmetals like chlorine tend to have a high electron affinity, and so they want electrons. And so what happens is that an electron from here will go to there, and now we've got these opposite charges, and of course that brings them together. And that's what ionic bonding is in a very simple review. Coulomb's law. Now Coulomb's law is a way to represent the energy involved when ions are coming together or breaking apart. So we've got this little equation, and I've got to tell you honestly, in AP we don't spend time calculating this out. It wouldn't be too tough to calculate it out, but we just don't spend much time because it's much easier to just compare ionic compounds. But let me just show you how it works. So we've got this value, joules dot nanometers, and so what Q1 and Q2 means is the charge. So imagine that would be a sodium charge would be +1, and a chlorine charge would be a -1, and let's say the distance in nanometers between the two was like 200 nanometers. So if I were to multiply those two together, I'd get a -1, divide by 200, times that by this number, and I'd get some energy value in joules, right? But again, to be honest, we really don't spend a lot of time calculating that out. The important thing is that you do get an energy value, and it's negative, which means that energy is given off. All right, so and again, that value, that negative value, just tells us that it's a favorable thing, right? What about the other kind of bonding? Covalent compounds. Okay, so notice that covalent compounds are simply just electrons that are attracted to the nucleus of one, and vice versa. So let's say I have an atom here, and there's another atom. Let me draw a different color atom. Try and make this a little unique. All right, so the nucleus of this atom is attracted to the electrons of that, and the nucleus of that is attracted to the electrons of that one. What kind of forces are going on here between the electron cloud and the electron cloud? They're repelling, right? And then what kind of forces are going on between the two nuclei? The two nuclei are repelling. And so there is some point where you get just the right combination, and that's where we get a bond. Okay? And so I've got a couple pictures here, and if you don't worry about writing this down, but if you want to look at this, you can definitely see this in your book. But the distance that we get right here, as I just wrote, that right there, that is going to be that's known as the bond length right there. Oh, yellow is not the right color for that. Okay, so here's a diagram. So imagine two atoms, not ionic compounds, but they're two nonmetals. They come together. They're getting a little closer. Now notice what's happening to energy. Here we have a zero energy. When they are by themselves, they have a certain potential energy. And so as it goes down, notice that they're getting closer and their energy is decreasing. Why? What's the driving force? Well, the driving force is to have a lower energy, right? And so down here you have a lower energy than you have up here. Up here we have a higher energy. Okay? So this right here is just the perfect spot, and that distance between those two atoms is called the bond length. Now imagine if we were to take those atoms and squish them together. That's not very favorable either, because we're looking for a spot that is just right between the two atoms that give you the maximum attraction between the nuclei and the electrons, and the minimum repulsion between the nuclei and electron repulsion. So if we were to go up here and squish it even more, that energy is going to go up. So down here is a lower potential energy, up here is higher potential energy. So this is the favorable thing right here, and that's why that occurs. All right, so as far as covalent bonds, again, this is kind of review stuff. Electrons are shared in a covalent bond, and in between covalent ionic bonds there are polar covalent bonds, and we talked about this last year. And what happens there is, let's say I have an example they always use is hydrogen fluoride. Let's say we have an example like hydrogen fluoride. Well, in hydrogen fluoride, it turns out that fluorine is super electronegative. Okay, if you remember, we talked about that a little bit in the past, and hydrogen's more electropositive. All right, so if we were to draw an electron cloud around these two atoms, you might want to just draw it as an even circle. Okay, but in reality, since fluorine's got such a greater electronegativity, it turns out that the cloud is, I guess, let's say it's swollen around this side and then gets smaller. Okay, something like that. You guys know how my artistic ability is. But anyways, so fluorine's going to get a greater share, and that's what this is. The electrons are not shared evenly. So what happens is this side in this molecule is more negative on this side and more positive on this side. So this is not an ionic bond, and it's not simply a covalent bond. It's a polar covalent, because we have a pole, a negative pole, and a positive pole. And so, again, I've got some diagrams here that will kind of show us. Imagine these hydrogen fluorides floating around, and again, here's the little delta plus and delta negative, and we were to put them in an electric field. Well, as soon as we put a charge in the electric field, they'd line themselves up. Again, the positive side here would be attracted to that negative side, and the negative side here would be attracted to that positive side. So it's a molecule that has poles, but is not quite considered an ionic bond. Okay, I kind of misspoke here. I said we already talked about electronegativity, but we hadn't. Of course, so I can just defer to last year. We did talk about it last year. But electronegativity just shows you, which element has the greater tendency to have the electrons around them. And as a trend, although that says trend, let's imagine it says trend. All right, I went ahead and fixed this, but let's look at a couple things we have here. So the trend is as you go left to right on the periodic table, it increases. And again, if you remember that fluorine is the king, and he's up in the top right corner of the periodic table, and then decreases as you go down. And again, if you want to talk about the Y's, it's the same reason. We have electron shielding involved when we go down the column, and we have a greater nuclear charge when we go across. But anyways, that difference in electronegativity, and we have a chart that gives us numbers for that. The difference really tells us how polar it is. So you could have a value of, maybe we get a value of 1.0 versus something that is got a polarity difference of 0.7. Well, this is the more polar molecule than that one. All right. So I want you to look at this sheet here. You need a periodic table for this, but just predict which of these would have the greater electronegativity, and we'll see how you do. All right, is that what you got? Just as a quick review, we're going from smallest to greatest, and if you think about the periodic table, up here, strontium's below calcium, and that's below magnesium. So again, the trends are it increases as you go up, and it increases as you go that way. For GE, C, and F, GE's below C, and then F is, of course, the king. For TE, SE, and O, well, TE is at the very bottom, followed by selenium and then oxygen. And for P, N, and O, P is below N, and then oxygen's to the right of those. So there you go. Hopefully that's what you got. Now let's look quickly at kind of this this idea of what's going on with electronegativity and the bond type. When you have no difference in electronegativity, that's when you have your covalent bond, or as last year we called it, a nonpolar covalent bond. When you have a little bit of difference, and again, the scale is not a really big deal. I'm not sure what your book talks about. We just want to keep in mind that, let's say this number goes from 0 to 3, all right? So intermediate somewhere in there, and then if you've got a big difference, that's an ionic bond. But the important thing is this is really, they're using this word ionic character, and that's really the best way to look at it. Okay? The more the difference is in electronegativity, the more ionic the bond is becoming. Again, it's not like these molecules know, oh, I'm an ionic bond or I'm a covalent bond. This is something that we've made to help us kind of understand how things are going. So one more little practice and then we'll be done. All right, rank the following bonds in order of increasing ionic character. Take a moment to do that. Okay, now doing this without a periodic table is tough. Doing this without doing it without a periodic table would be really tough unless you kind of had it memorized. But doing it without a chart, you just kind of have to get a general idea of what's going on. So we've got this P and S. Now these are both nonmetals, right? So this is going to be pretty nonpolar. Or, pardon me, it's going to be a little bit polar. Okay, strontium and sulfur, you've got a metal and a nonmetal, so that's going to be an ionic bond. Carbon and nitrogen, right next to each other on the periodic table, that's going to be polar. This is going to be two atoms, the same element, that's nonpolar. And then sodium and chloride, those are at opposite ends of the periodic table, so they're going to be ionic. And if we were to have to put them in order, separate this P from this P and this I from this I, it really would be tough without an electronegativity chart, which we're not looking at yet. So there you go. See you next time. Hope this was okay. Any questions, ask me in class. Bye.